So in this video, we're going to talk through the formulas for doing confidence intervals for beta, for theta, actually, and as well as for the probability of success. In the next video, we'll actually do the examples to these confidence intervals, but right now we're just going to focus on the formulas and sort of understanding why these are the formulas that we're going to be working with. All of the intervals that we're going to be talking about are going to be walled confidence intervals. And I don't want you to always think that walled is always a bad thing. There's definitely some good things with it. And also many times the walled can actually give you a pretty good confidence interval. There's a lot of times with proportions, they haven't been the best intervals to work with. So first, let's just think about what, for beta, our slope-ish looking parameter, what its walled confidence interval would look like. So what I'd want to do is I'd want to take my estimate, which would be beta hat, plus or minus our z, which would be based upon our confidence interval, times some type of standard error. More specifically, in this case, the standard error is going to be the square root of the estimated variance of beta hat. Now, many of you have talked about variance in previous classes, but not everyone has. So kind of a real quick as an aside for those that have not done a variance before. So when I have a variance, that is the same thing as either like a standard deviation or a standard error squared. And so since I really just want a standard error, if I took a square root of a variance, that's going to give me a standard error. So it might seem a little weird of, well, why would I write things here in terms of variance if I'm really going to end up taking the square root of it in the end? Well, the reason is because I can actually find this estimated variance of beta hat in R, but it doesn't directly give me the standard error of beta hat in R. It actually is, but we'll actually show you where that is later. But this will be nice because it'll be stored for us. Next, I might want to do a confidence interval for our odds ratio, theta. So if I'm looking at theta, we kind of had two different estimates that we had based upon what kind of variable x was. So in one case, we had x being only a binary variable, so where it could only take on the values of 0 or 1. And if you recall as well, to kind of understand where this is going to be coming from, that our theta hat in this case was just e to the beta hat. That's how we found it. So what my confidence interval is actually going to look like is it's going to be this same formula I have up here, except for now I've raised e to that power. So if I take e to the beta hat plus or minus z times the square root of that estimated variance of beta hat, that will give me my confidence interval. Now instead, when x was continuous or quantitative, we might have that c show up. So not necessarily just increasing x by 1, but allowing x to increase by c. So when we did that, our theta hat was just e to the c beta hat. So it's going to make my formula for the confidence interval look a little bit different. So it's going to be e to the c beta hat, which probably makes perfect sense, plus or minus z times c times that square root of the estimated variance of beta hat. So a big difference here, and the easiest one to lose, is that that plus or minus part includes the c being multiplied in there as well. We're going to review why that's actually true for our math and stat majors here in just a moment. So we will talk about where that C is coming from. As we saw with our first example, though, sometimes we wanted to look for an interval for a decrease in C units instead of an increase in C units. So what, of course, I did there first is I estimated by inverting my actual estimate. So we took 1 over, which then means if I'm looking at my interval from up here, it's going to be 1 over upper becomes your lower, and 1 over the lower would become your upper, because they're now going to flip places once I've inverted it. Because, of course, I want to have the smaller value here and the larger value here, so it ends up flipping spots once we invert them. Again, for my math and stat majors, or those that have taken like a 250 class, why does that C appear next to our estimated variance of beta hat? Well, as a little refresher, if you remember from that class, you could find the variance of AX plus B was A squared times the variance of X. So if I need to find the estimated variance of C beta hat, that's going to be C squared times the estimated variance of beta hat. And so then if I take the square root of this to get my standard error, that C can pull out front, and we would leave the estimated variance of beta hat under the square root symbol. So that's where that C is coming from up above here. Now again, that's just more of to explain why it's coming there. Just make sure we don't forget that that C is there. So sometimes C can be 1 and then it kind of feels like it disappears, but it's easier to kind of always feel like that C is there whenever X is continuous or quantitative. The last interval I want to talk through is actually doing a confidence interval for pi of X, or that probability of success. Now, we did one before that's not actually as good, and in our actual next video we'll talk a lot more about why that interval is actually not the greatest that we did before. But here is what I know, right? Already we have found that if I wanted to find pi hat of X, I took e to my alpha hat plus beta hat times X over this 1 plus the e raised to it. And one of the reasons why I like this is it forced numbers to be between 0 and 1. So I kind of really feel like I should be using something of this type of form when I'm actually doing my confidence interval as well. So what it looks like is probably not a huge leap here. So we're going to take our e to our alpha hat plus beta hat X. But then that we are going to plus or minus by our z times our estimated standard error, which is the estimated variance of alpha hat plus beta hat times X, over 1 plus the same thing. One small thing to make note of in case you were ever doing this or trying to kind of verify it by hand is if I use the plus sign on the top, I'm going to make sure I use the plus sign on the bottom, minus sign on top, minus sign on the bottom. So there's only 2 numbers we're going to use. Just make sure that the same ones match as we're doing it. So the goal of the next video is to take these formulas and show you, one, how to actually get these values in R, and then of course also how do we interpret these confidence intervals that we get.